Hey everybody, welcome back. This is video 2 for week 10. The topic is conjugacy. And so in the last video we talked about symbolic dynamics as a way to show that a certain map is chaotic. In this video we're going to use a different technique by establishing a topological conjugacy between two maps to verify that a given map is chaotic. I'll see you on the next slide. Really quickly, before we get to the topic of conjugacy, I want to talk about our good friend, the tent map. So we keep coming back to this over and over again this semester, and we keep alluding to the fact that it's chaotic. So our tent map, T, goes from 0, 1 to 0, 1. It's defined here as a piecewise linear function, and here's the graph of it. We can actually show that T is chaotic using symbolic dynamics. In the last video we did Baker's map instead of the tent map. And the reason why I did this is the use of symbolic dynamics for the tent map is a little bit more complicated than the one for Baker's map. I have posted a PDF on Husky CT if you want to check out how they actually verify that. So again, you have to use the definition of Devaney and symbolic dynamics. The PDF I showed you actually goes through and verifies all three properties, whereas transitivity is the only one that's necessary, but they do go through all three properties. And the approach that they use is more complicated, as I stated, but nonetheless, that same method of going to sequence space and using the shift map can be applied to the tent map to show that it is chaotic. So at this point in time, as we proceed with this video, we are going to assume that we know for a fact the tent map is chaotic and that Baker's map is chaotic. It can also be shown that that shift map is chaotic. So we kept using the shift map, and you can actually show that that verifies those three conditions as well. So in our repertoire, we have now three maps that we know are chaotic. As we proceed with this video, we're going to find conjugacies with other maps to known maps that are chaotic. And that's the idea. We relate other maps to the maps that we know are chaotic, and we show that they must also be chaotic. All right, so here's the idea we're going to explore today. Suppose you have a map F going from an interval in the real numbers to the same interval in the real numbers that produces a difference equation, x sub n plus 1 equal to f of x sub n. Now, we run some simulations on this difference equation, and we find that we suspect it to be chaotic. So we're either observing sensitive dependence, or we're observing the onslaught of periodic points. We might observe a period 3 orbit. So we might have a suspicion that it is chaotic. And the question is, what do we do? How do we verify this? So you have two options, really. Number one, you can attempt to show directly that that map is chaotic. So you can actually apply Devaney's definition. Since we're on the real numbers, we only need to show transitivity. So you basically just need to show that this map is transitive, or that it has a single dense orbit. Now, you can do that with symbolic dynamics. You can do it with any other mathematical approach that you can come up with. You can be creative. There are a lot of different approaches that people use, but the one we saw was symbolic dynamics. Sometimes that's easier said than done, so we have to resort to this second method, which we'll discuss today. And that is to transform, and I put in parentheses, in a special way, because it's going to be a special transformation, our function f into another map G that we know is chaotic. And provided that we do this transformation correctly, the property of chaos is preserved. So I'm going to define what that transformation is. We call it a conjugacy, and we're going to show that there's a result stating that chaos is preserved in that conjugacy. And then it amounts to basically just trying to create a transformation to get your function f to be one that we know something about. All right, so on the left here, we would start with our function f from some interval I to I. We're going to do a transformation to create another map G from J to J. Now, I and J might be different. They might be the same. In the transformation, we're not necessarily preserving what that interval is, and we don't necessarily need to. So to do the transformation, we're introducing this transformation phi that's going to take us from the interval I to the interval j. You can imagine that this is just a change of variables. So for example, on the left, if we were working with f, if we were using x's over here, on the left we're going to use, say, y's over here, where x is in the interval I on this side, and y is going to be in the interval j on this side. The change of variables in the middle to get us between the two is just going to relate x and y. So it's going to be a relationship between your two variables. Now, in order to preserve, so as we do this process, in order to preserve our properties, we need to make sure that phi, so that this little guy phi, satisfies certain conditions. It turns out that that function phi, the transformation, has to be what we call a homeomorphism. Now, phi is going to take an interval I to an interval j, and a homeomorphism is defined as a mapping that satisfies three properties. The three properties are that phi has to be one-to-one onto, and that phi and its inverse are continuous. I recognize that some of you might not be familiar with the words one-to-one and onto, so on the next slide I'm going to give you an overview of what that means. But for our purposes on this slide, understand that this transformation, in order to preserve topological properties from the map F to the map G, this transformation phi had better be a homeomorphism. If it is a homeomorphism and we're able to relate F and G, then all properties are satisfied, or are preserved, and particularly the property of chaos is preserved. So it's going to preserve sensitive dependence on initial conditions, density of periodic points, and transitivity of the maps. Okay, so one-to-one and onto. Let's talk about one-to-one on the left side of the screen here. For the transformation phi from I to j to be one-to-one, here's the official definition. For any 2 points that you take from the first interval, if the images under those 2 points are equal, then the 2 points had better be the same. What this means in practically speaking is that the mapping, when you graph it, passes the horizontal line test. So anytime you pass a horizontal line through the graph, you will not hit 2 points. So for example, if I were to draw you this function like this, and we're just looking on the real line, this, if I took a horizontal line at any point, it's going to hit 2 points. So there's an x1, there's an x2 that have the same image. So here's your phi of x1 and phi of x2. They have the same image, but they're not equal to one another. So this is not one-to-one. Whereas if I drew another picture here and took a line, let's say, any horizontal line that you pick, there's only going to be 1 point that goes to that image point. So phi of x1 is only achieved through 1 point in the domain. All right, so the pictures are really the easiest way to understand this. Understand that this is not one-to-one because there's a point where you have 2 points that have the same y value, and this is one-to-one. Just to give you another example, I can draw, say, a graph that looked like this, and then kind of doubled down on itself and then went up. This one is not one-to-one because, again, it fails it in the middle here. There's several points that all have the same image. All right, so these two are not one-to-one, and this guy down here is one-to-one. Moving on to onto, if you take any point from the codomain space J, so you take any any point Y, then there must, so this is for all Y in J, there exists an X from the domain that maps to that point Y. Okay, so suppose my I, just as an example, suppose my I is 0, 1 and my J is 0, 1. Well, then I can graph it. So we'd be going from 0, 1 to 0, 1. And suppose I graphed you a function that looked like this, kind of like my logistic map. This is not onto. So think about, you have your I down here and you have your J interval up here. There are points in the J interval, all these points up here, that are not mapped to from the interval I. So, for example, the point if y were equal to 0.8. There is no x such that phi of x equals 0.8. So this doesn't actually exist, and that's why it's not onto. So this picture would be of the function phi. Whereas if I drew you another diagram of the same situation, 0, 1, 0, 1, and I was able to, cover the entire, basically you're looking at the y-axis and seeing if the graph actually covers that entire interval from 0 to 1, and in this case it does, so that would be onto. To better understand the concept of a homeomorphism, I'm going to give you three concrete examples here. So example 1, all of these are homeomorphisms. If you have a phi going from -1 to 1 to -1 to 1, and you just take a power function, x to the n, provided that n is odd. So, for example, go off and graph x cubed. And if you graph x cubed, you'll notice that it is 1 to 1. It is onto on the interval from -1 to 1 and -1 to 1. And you'll also notice that the function and its inverse, so the inverse would be the cubed root, are continuous. Same sine of x and cosine x, going from 0 to pi over 2 up to 0, 1. Those are 1 to 1 onto and have continuous inverses. And same with this trigonometric function down here. So verify that, graph those, make sure you can see how the three properties of a homeomorphism come into play for those. So now we have the idea of a homeomorphism, but how do we connect the two functions? So I've got f on one side from I to I, g on the other side from j to j. I know I need to connect them with a homeomorphism or a transformation. What does that mean? So this definition, if you have f and g are said to be conjugate maps. All right, so there's this term conjugate. And actually, before conjugate, so our book only uses the term conjugate, but in mathematics in general, we would put topologically conjugate. So this is a topology concept. They're conjugate maps, and the notation we use is that f, we use these, the squiggly equal sign. That's what that stands for, conjugate. If there exists a homeomorphism, phi, from I to j, so we know what a homeomorphism is. It has to be 1 to 1 onto, and it and its inverse have to be continuous, such that phi composed with f of x is equal to g composed with phi of x for all x on your interval I. In that case, we get two maps that are conjugate. And we'll talk about what that means to be conjugate. But I'm going to pause the video because I want to actually discuss this condition a little bit more and why that is super important for us to get a transformation from f to g and what that means for us. So to explore this condition a little bit more, I want to take the left-hand side and the right-hand side, and we're going to talk about what each one means and see how that is important in the concept of conjugacy and having a homeomorphism. So let's check out the left-hand side. We start in an interval I, so I'm going to draw two i's here, and we start with a variable x. So I'm looking at this condition here. I'm starting with an x, and the x comes from the interval I. I then apply the function f. Remember, f goes from I to I. I apply the function f to that starting place x, and I get the function value f of x. So that's my normal map. That's the map that we're trying to find out something about. What we want to do, remember, the ultimate goal is to transform this map, right? We want to transform this map down to an interval j where I have a different function, g, working on those new intervals j to j. I want to transform this and preserve all the topological properties. So watch what this left-hand side is saying. I start with x, which I did there. I apply f of x, so now I'm over here with f of x. And then I apply this transformation map phi, which is going to allow me to make this transformation, make this jump down. So I go from f of x over here, and phi takes an element from f of x and brings it into j. So I actually end up with phi of f of x. Now the right-hand side of this conjugacy equation, so this equation, the right-hand side, starts with an x in I, so we're going to start at the same point that we did before. You then evaluate it with phi, so we're going to take this x, hit it with phi, which brings us down to j. So this is your phi bringing you down this way. And again, phi brought you down this way before as well. You'll get to j, so now that's phi of x down here. And then you apply g to it, so you end up with g of phi of x. And in order to be a conjugacy, what is required is that these two things are equal. So we take two different routes to get to the same place, and what's effectively happening is we are making this transformation from f down to g by way of this function phi. All right? So imagine before we lived up here in f, this is where we were living before. We want to live down here with g, and in order to do that, we take the original x and we make it a phi of x. So instead of doing f of x, we're doing g of phi of x. So that's your transformation, that's your change of variables that allows us to now study g instead of f. And then one final note here, the homeomorphism phi is so important for this conjugacy that up in the notation, we actually use a subscript with the phi. So you'll put that f is conjugate to g via the homeomorphism phi. So one important point, guys, I want to point out involving conjugacies, this is the equation that we had from the last slide. This is really a compositions of functions. So this is really phi composed with f is equal to g composed with x. So we can actually drop the x's and express it in this notation. Now, if we apply an inverse of phi on the left-hand side of both sides, so a phi inverse here and a phi inverse here, you're left with just f on the left and phi inverse composed with g composed with phi. This is the formula that you'll see for topological conjugacies in most textbooks. So f is topologically conjugate to g under the homeomorphism phi if you have this being satisfied. The reason I'm bringing this up is this should ring a bell from linear algebra. You saw this with change of bases, you saw this with diagonalization techniques, where you took a matrix and you found a permutation matrix P. So this should ring a bell if you, from linear algebra, if you had a matrix A and you could write it as P inverse dP, where A is your original matrix, D is your diagonal matrix, and you've got your permutation matrix flanking the D. The permutation matrix allowed us to take an arbitrary matrix that we wanted to study and convert it in a special way to preserve all the properties, especially the eigenvalues of that matrix, using this permutation matrix P. So in our context, the A, the original matrix you started with, that's your function f. The D is the function g that we want to actually study. That'll be easier for us. And the P inverse is your phi, your homeomorphism. So now that we have the idea of a conjugacy, we need a theorem or a result that shows us that having a conjugacy between f and g is going to preserve the fact that one of the maps is chaotic. So if you have a map f from I to I, and it's phi conjugate, so that means f is conjugate to g via the homeomorphism phi, then f is chaotic on I if and only if g is chaotic on j. So if g is chaotic, that means f is chaotic. If f is chaotic, g is chaotic, provided that you have this homeomorphism that is creating a conjugacy between f and g. All right, so here comes the exciting part. We are finally going to be able to show that the logistic map with the parameter equal to 4 is chaotic on the interval from 0 to 1, and we're going to use conjugacy. All right, so this is the logistic map. I explained a couple videos ago that you have to have the parameter equal to 4 to actually have chaos, meaning to have those three properties, or we really just need transitivity. But to show that that's chaotic, we're going to form a conjugacy between that map and another map that we know is chaotic. So how do we pick that other map? And what I've done here is I've drawn your logistic map. So this is the graph of 4x times 1 minus x. It goes from 0, 1 to 0, 1 on the x-axis and on the y-axis. And I want to come up with another map that we should try to form a conjugacy with this map. And the best map, you're probably all thinking it, is the tent map. So you'll notice that the reason why this is a great choice is because the tent map looks very similar in shape to the logistic map. It's just a sharper corner at 1/2. All right, so we're going to try to find a way to transform this map F to this map T using a homeomorphism, and we'll talk about that on the next slide. So what we're going to do is we're going to compare that logistic map with the tent map and try to form a conjugacy with some homeomorphism phi. So just so you guys are aware, this is our logistic map, which I've written here. It goes from 0, 1 to 0, 1. And the tent map is a piecewise linear from 0, 1 to 0, 1. So our job is going to be to take a homeomorphism phi that goes from 0, 1 to 0, 1. So in this case, the I and the j are the same for both. And we have to show two things. First, we have to show that phi is a homeomorphism because we know that this, to get a conjugacy, you first need a homeomorphism phi. And remember that that homeomorphism has to have 3 properties. Then, once you show that the phi that you've come up with is a homeomorphism, the second part is to show that F is conjugate to T through that homeomorphism by showing that phi of T of x is actually equal to F of phi of x. Now, you'll notice, the spots where you put these functions is kind of arbitrary. So what we're actually doing here is showing that T is conjugate to F, but it doesn't matter which way we do it. But I'm writing my condition in this way, so I'm forming my homeomorphism so that I can get this requirement. All right, and we're actually going to do this. We're going to go through and we're going to show that a given phi, which I'm going to provide to you, is in fact a homeomorphism, and that it is also a conjugacy, allows for conjugacy between F and T. One of the hardest things to do with this whole process is actually determining what function to use as your homeomorphism. And there's no real prescription for that. There's no real procedure to find that. It's very, very heuristic in the sense that it's almost like a guess and check. But the one that works for the tent map and the logistic map is this function here, sine squared of pi over 2 times x. And I've graphed it. All right, so I'm going to give this to you, and we're just going to verify that it does what we need it to do. So the first thing that we talked about in the last slide is we have to show it's a homeomorphism. So there's the 3 properties of a homeomorphism: 1-to-1, onto, and that the inverse is continuous, and the function itself is continuous. So let's just verify 1-to-1 and onto for this graph graphically, for the function graphically. So we're only working on the interval from 0 to 1, so the only part of this graph that I care about is this part here. Okay, you'll notice that it is 1-to-1 because any horizontal line that I pass through this graph is only going to intersect the graph at one point. So all these horizontal lines are only going to intersect it at one point. So it is 1-to-1. It is also onto because the entire interval from 0 to 1, the entire interval from 0 to 1 here, is mapped to from the function. So you do have y values that are achieved all throughout the interval from 0 to 1. So we have 1-to-1 and we have onto. The next step is to find the inverse and make sure that it's continuous. So to find your inverse, remember the procedure. You have your function y equals sine squared of pi over 2x. You flip the positions of the x and the y, and then you need to solve for y. So we'll take a square root of both sides. We will then take an inverse sine of both sides and multiply by 2 over pi to solve for y. So this is your inverse. So this is phi inverse of x. All right. And sine inverse of root x on the correct domain, which we are on the correct domain, is in fact continuous. So we're all set with the three properties of the homeomorphism. So what we can do now is check that f and t are conjugate under this homeomorphism phi by just checking this simple property, this equality here. Phi of t of x has to equal f of phi of x. And what I've done is I've put up your three functions here. So all we're going to do is show that the left-hand side of this equality is equal to the right-hand side. We're going to need to use some trig properties. I'm going to put the trig properties at the bottom of the page here so that we can reference them. So there's our nice refresher. We have three trig identities we're going to use in this computation. But nonetheless, let's start on the left-hand side. So we're going to take phi of t of x, and I have to break this up into two cases. So the first case is if x is between 0 and 1/2. Now in this case, t of x is just 2x, so you end up with sine squared of pi over 2 times 2x, which is just pi x. So this is what we end up with under that case. And then if x is between 1/2 and 1, phi of t of x is going to be equal to sine squared of pi over 2, and t of x is 2 times 1 minus x. So of course those 2's are going to cancel, and we end up with sine squared of pi minus pi x. And by one of my properties down here, by the second property, a translation and a flipping of sign will actually leave us just with what you have here when I have a pi translation. So this is sine squared of pi x. So we end up with the same thing, which is good. So in either case, I get sine squared of pi x on the left-hand side. Now let's go on over to the right-hand side, and let's see what we get for f of phi of x. All right, so f of phi of x, f is 4, phi of x is sine squared of pi over 2x. So you're getting all this, 1 minus sine squared of pi over 2x. And we need to simplify this. So the first part, this we can use our trig identity down here. So that's just cosine squared. Next, we can actually rewrite this under 1 square. And finally, we can use our third trig property right here, which we're going to use on this one. So we end up with sine of 2 times pi over 2x all squared. And so this is sine squared of pi times x. So essentially what we've shown is that yes, this condition up here is true. The left-hand side is equal to the right-hand side, which means that our two maps are conjugate to one another under the homeomorphism that we defined on the last slide, and therefore they preserve all topological properties, including chaos. So this shows us that the logistic map is chaotic. And that's a really cool result, guys. So if with the parameter equal to 4, our logistic map is chaotic. We talked about that in the last video, but now we have finally shown via a homeomorphism and a conjugacy with the tent map that this map is chaotic. And I want to point out one more cool thing before we finish with another example. The tent map, so we showed in the last slide that that phi of t of x, so phi of the tent map is equal to f of phi of x. This means that t of x is actually equal to phi inverse of f of phi of x, like that. You can actually take the logistic map, compose it with sine squared of pi over 2x, and then compose it on the outside with the inverse of sine squared of pi over x, and get the tent map. That's a super cool result. Try it out. It's like a little algebraic technique. It's going to be part of your homework. So it's super interesting how we can get from the logistic map to this, but part of your homework is going to be to show this relationship. I'm actually going to end this video here, guys. So we will have a third video for this week, and I'm going to talk a little bit about some more examples of conjugacy. So it'll be a shorter video, but I do want you to do a daily question for this specific video. I really enjoyed reading your summaries last week of the lecture. So what I would like you to do is go on to Husky CT. There will be an assignment there for the DQ video 2 of week 10, and I just want you to summarize what we just did. Try to be as brief as possible, but also make sure to hit all the points that we discussed. And I think that's a really good exercise for you guys to go through. All right, I'll see you in the next video.